Hi, my name is Shannon Good. I'm part of Team 25, SPK Fuel Solutions, and today we're going to talk to you about our design project for the conversion of sugarcane into jet fuel. First, I'm going to go into some background about the scope and the chemistry of our project, and then we're going to talk a little more about the process design, the economic evaluation, and then our final conclusions and recommendations. So first off, why is it important to start considering sugarcane as a fuel as opposed to the typical kerosene production? So this graph here shows from the EPA that there's a trend in CO2 emissions continuing to skyrocket due to the increasing use of fossil fuels. This is really an issue because it's linked to global climate change. So there's a big push globally for different governments to try to limit this amount of CO2 emissions. And one of the big ways to do this is to try to limit the use of fossil fuels. So sugarcane gives us this potential to use something that might not emit as much carbon dioxide. So why does it limit the amount of carbon dioxide? So sugarcane is part of a closed loop carbon dioxide emission cycle. So as you can see in this figure, carbon dioxide is absorbed by the plant and it's growing, and then when we convert something like sugarcane into a jet fuel, the carbon dioxide that is then emitted is basically the same amount that was absorbed in the first place, leaving a net zero emissions of carbon dioxide. So there, the only carbon footprint we'll see is the energy we actually use to convert the sucrose or the sugarcane into our jet fuel. And this will really help limit the carbon emissions and hopefully the challenges with global climate change. So there are a lot of different ways to actually go about making jet fuel from sugarcane. There's a lot of research being done right now. As you can see in this figure, it's pretty crowded. There are many different ways to make jet fuel from sugarcane. Not all of them are very feasible or efficient, but basically you can either use sucrose or you can use bagasse. Sucrose is more so like the ethanol industry, where using bagasse is more like a cellulosic ethanol technique. And that really has a lot of efficiency problems, so we decided not to go this route over here. So we considered more of the fermentation routes. We did some research and found that ABE fermentation has a lot of problems in industry with separations and efficiency. So that left us with this route over here, which goes through a fermentation and produces a C12 jet fuel. It's a pretty straightforward method, and that's part of the reason why we decided to go with that. So finally, this is the end-all chemistry we decided to go with. And in the end, we came up with a plant capacity of 3,810 gallons per hour of our C12 jet fuel at a purity of 99.95%. So really what happens in this process is we take our sucrose, we put it into our fermenter, and we get out 2,3-butadiene, as you see here. We then put this through a dehydration to make our ketone, MEK. This MEK is then added into a trimerization reaction where we get a C12 ketone. And then finally we go through a hydrodeoxygenation process under high pressure with hydrogen, and we get our final jet fuel product. So now I'm going to pass this over to Tom, and he's going to go into a little bit more of the process overview.
All right, this is the process flow diagram of our overall design. There's 5 fermentations, followed by 10 rotary filters in parallel, which then have a storage tank and a flash distillation, followed by 2 distillation columns in parallel, which then goes into the dehydration reaction, which is then distilled, goes into the trimerization reaction, separated using a liquid separator, goes into the hydrodeoxygenation reactor, which is separated again and then distilled twice to a pure product. We'll go through each unit in a little bit more detail. So we have 5 different 500,000 gallon fermentation tanks where sucrose is fed into the tank. Bacteria will ferment it into 2,3-butanediol. It then feeds to 10 rotary filters in parallel. These remove all of the cell mass and most of the liquid from the reactor, which is then fed into a storage tank which holds a little bit more than one fermenter's worth of volume, just in case a whole fermenter needs to be emptied. So this goes into a flash distillation, which removes some of the water from the fermentation, and then this goes into 2 distillation columns in parallel, T400 and T410. This is a very energy intensive distillation. And we explored other methods of separation, but distillation was the most readily available technology, so we chose to do that. Following this, there's the dehydration reaction, which removes the water from the butadiol to form methyl ethyl ketone, which is then fed into a distillation column, which has an azeotrope, which makes it very high separation, very difficult, or losing very little MEK at the bottom. So following this, there's the trimerization reactor, which takes 3 methyl ethyl ketone molecules and forms one C12 ketone, which has a ketone functional group and a double bond in it. The water formed by the reaction and the C12 ketone are then separated by a gravitational separator. Water flows out the bottom and the C12 ketone flows out the top. This goes into a hydrodeoxygenation reactor, which has hydrogen gas fed into it, which removes the ketone and the double bond to form our C12 jet fuel. The jet fuel is separated from the water formed by the reaction in the same method that the C12 ketone was removed. And then there's 2 distillation columns at the end, T800 and T900. 800 removes methyl ethyl ketone, and T900 just purifies the product so it reaches our specified purity.
So after designing our process, we decided to do our economic evaluation just based on the price of jet fuel and sucrose. Currently, the jet fuel prices are $1 per gallon, which is about 18 cents per pound, and sugar prices are about 15 cents per pound. From this data, we have only 3 cents per pound to pay for our utility and other operating costs. The jet fuel prices are low because of the higher supply of jet fuel currently, but it might get higher. The total cash cost is about $1 per pound of jet fuel produced, and as you can see over here, the raw materials takes up about 72 cents per pound due to our fermentation technology, which only converts about 0.5% of sucrose. And as the fermentation technology requires a lot of amount of water to dissolve the sucrose, it's a really high intensive process. Thus, we have our utility cost about 20 cents per pound. Our total plant cost is about 194 million, and the IBL accumulates to about 94 million. The fermentation and the filtration technology is almost half of the IBL, the other 100 million is of OBL and other operating costs, and we have a project contingency of 25% as it's a relatively new process. So to achieve a rate of return of 15%, after-tax rate of return of 15%, we require our jet fuel to be sold for 120 cents per pound. If we want higher rate of return, we would require our jet fuel to be sold for higher prices. And based on current market, we don't think that our process will make any money. If a better technology is available to convert our sucrose to butanediol, for example, if the fermentation technology is able to achieve a 0.8% conversion, we would only require our jet fuel to be sold for 80 cents per pound to achieve a 15% after-tax rate of return.
So now I'm going to take you through some of the outstanding issues and recommendations that we have after completing this project. The first one, and probably the biggest one, is our fermentation, which was probably the biggest challenge in this entire project. Currently, we are compressing a lot of air so that the culture that we're using can survive. It uses the oxygen. One of the things that we were thinking about is potentially using pure oxygen instead of air, and that way we would have a lot less volume of gas to compress, but pure oxygen is more expensive. So it was a trade-off deciding whether or not we wanted to use pure oxygen or air, and in the end we decided to use air. Secondly, because our fermentation chambers are so large, there are some concerns about mass and heat transfer issues and mixing in the fermentation chamber to make sure that all the culture was getting all of the nutrients that it needed, and making sure that everything was mixing and well distributed within the chamber. Another one dealing with the chambers was how long they would take to clean and sanitize. Because of how large they are and how much stuff is in there, we need to drain them, clean them, sanitize them all in a good amount of time so that we can recharge them and begin to produce more of our 2,3-butanediol. And finally, we're assuming that the CO2 that is being produced by these cultures is being purged continuously. That may or may not be the case, and we just are assuming that without really knowing whether that might be true or not. So a couple issues, once again, outstanding issues we have are whether or not companies will actually consider mixing our jet fuel with their blends. They have such strict restrictions with the Jet A that is currently on the market that we don't have enough information and research about our own jet fuel to be sure that it is actually up to those standards, such as boiling point, water content, cloud point, heat of combustion, other specifications that we're not sure about because we didn't have the time to do the research, and whether people will actually want to blend this in with their jet fuel. And finally, because the process is so expensive, it takes a very large government subsidy for it to be economical at all. So we really don't know whether or not this process, even though we can make this jet fuel, whether or not it's worth it in the end because of how uneconomical it is.
So after working through our full plant design and economic analysis, we've come to the conclusion that at this point, it does not make sense to build this plant because it's not economical and is really nowhere close to making money. And the reason for this is that the fermentation technology is still fairly new and in development. So the fermentation and purification are just too capital and energy intensive to make economic sense at this point. And there's a few things that could happen in the future that could change this. As we mentioned earlier, the jet fuel prices are at historic lows. So in the future, if jet fuel prices would begin to rise again, that would make this process a lot more attractive and potentially profitable. And also there's a lot of room for optimization in this process. One of the things we looked at in one of our alternative studies was purifying our leftover butanediol and just selling that to the marketplace. And that improved the economics as well. So we would recommend that more research into alternative processes would be done to see where else this plant could make money or where else costs could be cut. And in addition, in order for biofuels like our bio-derived jet fuel to become profitable, they're really going to need government subsidies. And governments have good incentives to do this as concerns about climate change continue to increase. Bio-derived fuels could become the future, so government support would go a long way towards making this profitable.